Hello, everyone. Welcome to the session today. Hope you enjoyed the previous sessions. Those who have watched would now know what happens behind the scenes on the cricket field when you're trying to live stream a cricketing event. So I have discussed about what are the various cameras, how the camera feeds are captured and sent back to the studios, and where they are mixed, encoded, transcoded, and then they're distributed over the CDN. Now, this is just one part of the story. Now, what happens in the OTT backend? How do the OTT servers work? And how does the entire thing of onboarding an user, billing him, enabling him to watch the live streaming on his particular device, be it a mobile phone, a tablet, or a TV, how does that work? So, we are going to discuss the system designs of an OTT architecture that will allow you to understand what the entire architecture of a OTT platform looks like, what are the various moving parts behind it, and how it works on the cloud. So today's discussion will be just that. So I'll be explaining what an OTT platform system design looks like, how does it work, what are the various important backend services, what are the front end services, how API layers work, if there is a middleware, what does that do, how it collaborates with the CDN layer, like how does the entire thing works as a well-oiled machine. So let's jump in and explore the system designs for OTT platform. So if we talk about the OTT platform, software architecture-wise, it mainly comprises of three main parts. The content delivery network, which we already discussed a bit, and then you have the other two parts. One is the client side. Say you're using an Android app to watch OTT platform, then it's your Android mobile phone. That's the client end. And there is obviously a backend, which is mostly a series of microservices. We'll come to that in a bit. But before we move on to understand the system designs architecture for an OTT platform, let's first understand what are the functional and non-functional requirements for a OTT platform architecture. Because once we understand the functional and non-functional requirements for that architecture, we can go ahead and build that architecture or design that architecture. So the functional requirements are the OTT platform should have a feature to allow users to create accounts and subscribe to a plan. So that simply translates to like if you are an OTT user, you want to say sign into a OTT platform like Stars Play or Netflix or Amazon Prime, you would need to create an user and subscribe to a plan and sign up. So that is a core functional requirement. The first functional requirement is that. So what I'm doing in this session is trying to explain you in plain English what the functional requirements for an OTT platform is, and then we'll move on to understand how to translate these requirements into technical architecture and how to design it, and then understand how all of that works together. And then we'll obviously fit in the live streaming cricket play into this architecture so that we understand how the architecture can scale up to provide services to millions of users who would be watching a live cricket match. So the first functional requirements going back is to be able to create user accounts and to be able to subscribe to a plan. Then the second is it should allow users to handle multiple accounts. That is for granted. And then it should allow users to watch videos, which is what the OTT platform is for. And then it should allow the company, OTT company or platform, to be able to upload new videos or video streams from the backend and make it available for the platform. What are the non-functional requirements? Well, one of them, and the most important one, is when somebody watches a video on a OTT platform like, say, YouTube or Stars Play or Netflix or Hotstar, there should be no buffering. That is, the user should be provided with real-time video streaming without lags, because the user experience is paramount when it comes to OTT platforms. And then the system should be reliably designed. It should be uh, highly available and reliable. And then the final requirement is it should be scalable. As the users grow or as the demand for streaming grows, the system should scale up in proportion so that all the users are able to watch the videos without buffering, without lag, and have a good user experience. So this is all we need from OTT platform at a very bare bones level. So how do we achieve that, and what is the design behind this? Let's go ahead and watch that. So as I said, OTT platform has an interactive user interface that works on multiple devices. This client-side application should be available to work on mobile phones, iPads, various models of TVs, laptops, and so on. So most OTT platforms have their web portal applications that would work in computers, laptops, and so on. And then they would have a iOS application that would work for Apple devices, iPads, and so on. And then there would be various applications that run on TVs, say Samsung Tizen OS applications. Then there would be LG Web OS applications, and so on. So there would be multiple client-side applications, and these would be thin clients in some cases, and in some cases there would be full-fledged applications. And even, yeah, I forgot to tell you about Android apps as well. So all these connect to the backend and then work to bring out the user experience for that OTT platform. Now, the portal applications would preferably be on Node.js, React.js platforms, because these kind of front ends have good loading speed, durability, and performance. Some older OTT platforms still use lightweight PHP front ends as well. Now, these are responsible for the layouts that we see when we log into the OTT platform, the entire user experience, various carousels with different movie types or series types or games or whatever is offered by the OTT platform that is available on the application end, the client side. And there would be features for searching video, and also the front ends provide features for intelligent video recommendations, which ease the users to enjoy their favorite binge watch. And then it would have other users, for example, when watching on a device, say on the mobile phone, you can continue watching the same application when you're back on a computer or any other device. And there are some specific user experience rules that are applied to make the entire client application very simple and intuitive to use. So that is how the front end side is designed. And then on the back end, mostly the OTT architectures I have seen work on a microservice architecture, because these are cloud native and easy to scale up. They have small manageable components at the API level, which enables the requests from apps and websites. And they have various other components that they use internally. We'll go deep into that, like how the backend is designed and how it works and what are the various moving parts. We'll go into that. But the one of the OTT platforms that I have worked with uses Java Spring Boot, and you use event driven databases like Apache Cassandra, and then Hadoop is also used, and then you use streaming applications, PubSub applications. So Apache Tomcat is used, and then you have RabbitMQ for PubSub, and so on. So backend services mostly provide few functionalities like user creation and authentication, event management, subscription management. Then there would be backend services for the videos, the video service, the transcoding service, and there would be a global search service as well. Now let's talk about the microservices backend. So the OTT services or OTT platforms architectural style is built as a collection of services or collection of microservices rather, and this is known as the microservices architecture and powers all the APIs needed for the applications and the web apps. Now, when the request arrives at the endpoint, it calls for other microservices for the required data, and these microservices can request data uh, to different other microservices, and it goes on. So after that, the complete response for the API request is sent back to that endpoint that requested for the original service. You can watch some of my other videos about microservices and monolith applications. I'll provide you the link in the description to understand more about the microservice architecture. All right, coming back to this, in a microservice architecture, the services should be independent of each other. For example, the video storage service would be decoupled from the service responsible for transcoding videos, which would again decouple from the service which is responsible for the, say, user creation and user identity. So how are these services made reliable? So how does that part of the architecture works? If you look into the diagram, you will see there is something called Zool and Hystrix in this application. So how does the connectivity work, or how does the load balancing work? When these kind of applications are hosted on, say, Amazon Cloud or Google Cloud, we use the elastic load balancers, and that is responsible for routing the traffic to our front-end services or back-end services. Now, the elastic load balancer perform a two-tier load balancing scheme, that is, where load is balanced over the zones first and then instances or the servers, which you can see in this diagram. And then the first tier consists of basic DNS round robin balancing, where the request lands on the first load balancer, and then it is balanced across one of the zones using round robin algorithms. And then another elastic load balancers is configured. So this second tier is an array of load balancer instances that performs round robin balancing again to distribute the request across the instances that are behind the same zone. So that is one kind of load balancer that is used here for this architecture. So there is another array of load balancers that is called Zool. Well, Zool is a gateway service that provides dynamic routing, monitoring, resiliency, and security. It provides easy routing on query parameters, URL path, and it has various parts as well. It has a NetTTY server that takes the responsibility to handle network protocol, web server, connection management, and proxying work. When the request will hit the NetTTY server, it will proxy the request behind the inbound filter. Now, what is the inbound filter? Well, in Zool, the inbound filter is responsible for authentication, routing, and decorating the request with headers and other stuff. And then it forwards the request to the endpoint filter. And the endpoint filter is used to return a static response or forward the request to a backend service, or the origin as we call it. And once it receives the response from the backend service, it sends the request to the outbound filter. And finally, the outbound filter is used for zipping the content, calculating the metrics, adding, removing the headers, and after that the response is sent back to the NetTTY server, and from there back to the client who requested it. So this is about the internal load balancer or Zool that is used in this OTT architecture. Then there is another component that is called Hystrix. Now, Hystrix is used for high availability management. Now, in a complex distributed server, a server may rely on the response of another server. So dependencies among these servers can create latencies, and the entire system may stop working if one of the servers or microservices fail at some point. So to solve this problem, Hystrix library is designed to control the interactions between distributed services, adding latency, tolerance, retries, and all this built in into the logic. So it stops cascading failures. It allows you to control latency. It allows to fail fast and rapidly recover. It allows to enable near real-time monitoring, and even allows you to cache your requests. So these are the various kinds of load balancing and routing methodologies used in OTT platforms. Apart from that, there is a service discovery application called Eureka. So that discovers where the endpoint or microservices is running in and sends that information to the Zool, so that Zool can properly route the requests to those endpoints. So now let's go into the grand plan and understand how this architecture looks like. So if you look at the left-hand side, there are various client-side devices. Now these client-side devices request the ELB or the Elastic Load Balancer, which we talked about some time ago. And in front of the ELB, you have the Zool, which are the API gateways for the microservices, and behind the API gateway you have Hystrix, and behind them you have the microservices running. Now these microservices would be Spring Boot microservices, for example, which I have come across in the OTT platforms. Now some of these microservices would be depending upon other backend instances like MySQL databases for relational DBs. There would be Cassandra databases for event information to be logged in, and there would be Kafka for event streams to come in, and there would be various kind of pub sub asynchronous calls that would be going through RabbitMQ or message queuing services, and so on. Similarly, some of the microservices would be responsible for transcoding and encoding videos. So they would also be using some kind of queuing mechanisms. And all this would also be having a layer of CDN. So you can see a CDN layer here as well in this diagram. So you can take some time and look into the flows of the flow arrows and understand which request goes on which direction and how it works. Now, this is not all. This is a heavily simplified diagram for an OTT platform, but that just serves the purpose, like how everything works behind the scenes or under the hood. Now, that is about the backend services. Now, if you are wondering how does the movie get ingested into the platform, or how a live stream get ingested into the platform. Now, the platform normally receives very high quality videos from production houses or studios. So these cannot directly be streamed into the customers' devices. So there are lots of processes that go on before they are made ready to be streamed into devices. And there would be more than 3,000 devices from various models, various manufacturers, TVs, mobile phones, tablets, and so on. So now these to stream to these 3,000 devices in different resolutions and formats, you need some microservices to be able to handle these operations. Now, basic operations around this are encoding and transcoding of these videos. I believe those who have watched the previous part of this series would know what it is. If you haven't, just follow the links below in the description and watch the previous part where I discuss what encoding and transcoding is. Well, so these microservices take care of the encoding and transcoding. Now, we also do file optimization for different network speeds. So that is also handled by this platform. And after transcoding, we have multiple copies of files for the same movie. And these files are transferred to each and every CDN that we have across various locations around the world. So what happens when the user clicks on the OTT application on his device? So first, what happens when the OTT application opens up? Um, the request would first go into the cloud platform where the OTT service is hosted, and there would be some backend calls such as login. And once the login is done, the authentication is done properly by the backend services, and the user would be able to log in, and then he would be able to see the front end layouts, and then the recommendation engine would come into play. So they would provide the recommended movies and carousels for his layout, so he would be able to view that on his screen. And then he can use search. So when he does a search term, so that search again goes into the search backend microservice. Then there would be various options to search the user's history, his home page, his billing information. So all that brings an interaction between his app and the backend service for the OTT platform. And that is how he's able to operate his application. Now, after that, when the user hits the play button on a video, then the OTT platform again sends the request back to the video handling microservices, which analyze the network speed and the connection stability. And then, when it figures out what is the best figure for that particular device and network, so based on that, the decision is made what is the nearest CDN server for the user, and the streams are forwarded from that particular CDN to the user device. Now, based on the device and the screen size and the network bandwidth, the video quality appears on the for that particular device and user. So you might have seen, like sometimes you see pixelated videos and slow videos on certain networks, and while on the same device you see a better quality on a better network. So all that decision making happens on the fly, and the user data is saved again in the backend databases, and other information such as viewing habits, location, reviews, likes, dislikes, everything is stored for that particular user. So that helps to build the recommendation for users, for that particular user, as well as other users who have similar likes and dislikes. Now, we use machine learning models to build this kind of a database, and in certain OTT providers, graph databases are used to build recommendations as well. Another important component in an OTT platform is caching. Now, caching can be done by Redis or Memcached, and those information which are most frequently used are cached so that the calls do not have to be sent back to the backend and overwhelm it. So the cache stores this in memory, and the responses can be sent back to the devices faster, and this enables the user to have a very good experience. So you can see the diagram of how the cache works, and for read-only information which is repetitive, caching helps a lot to increase the performance, availability, and reliability of the OTT platform. Now, as for the relational databases, mostly MySQL is used, and for NoSQL, Cassandra or MongoDB can be used. And these MySQL instances are mostly in a master circular replication mode with multiple read replicas, and again the read writes are split so that the backend requests, when they are overwhelmed, for example when broadcasting a cricket match or a soccer match, there would be a lot of read requests, then those requests can be sent to these read replicas while you can scale up the read replicas on the fly. That is how the databases work. And for the NoSQL databases, as I said, we use Cassandra, where you have a smaller storage footprint, consistent read-write performance. So storing events is very apt when you use Cassandra. So you can just scale it up and store multiple events on the go. So it allows to store things like live viewing history, which can be used for ETL jobs later on, and Also, compressed viewing history for older viewing records are also stored here. Apart from that, for the data processing, Kafka and Apache Chukwa is used. You can go through the repositories for these services to understand what Apache Kafka is and what Chukwa is. Now, Kafka and Apache Chukwa is used to ingest data which is produced in a different part of the system. Mostly these are used for error logs, UI activities, performance events, video viewing activities, troubleshooting, and diagnostic events. So that's what Chukwa is used for. Now, Kafka is nothing but for data streaming purposes. And these platforms also use Elasticsearch in a massive way for data visualization, customer support, and error detection in the system. Because as I said, all these are microservices. So there is a need of tracing a particular request, because one request may go through multiple microservices. So when there is an error, it is difficult to say what caused that error and in which microservice that error happened, because since all these microservices would be distributed across the system in various multiple Docker containers, so that is going to be difficult to detect. So in these cases, we use certain tools like ELK to do some tracing, and trace IDs are stored in the Elasticsearch databases, and Kibana is used for visualizing the errors and the logs for detecting where the error happened and tracing it back. Also, Apache Spark is used for movie recommendations as well, where machine learning models create movie recommendation, and Apache Spark is used for recommending content and personalizing them. So now if we consolidate, this is how an entire OTT platform looks like. So the architecture will have various high-level moving parts in the ecosystem. So you have payment gateways, OSS and BSS services, CRM and SMS services, campaign managers, ad servers, ad networks, recommendation engines, and analytics platforms. Now, these are all pluggable into the main engine. So the main engine would have business requirements, data requirements, user experience, IP and video control. And there would be another layer that would be taking care of content acquisition, encoding, transcoding, encryption, packaging, pushing it into the CDNs, recording events, storing it, archiving it, and so on. So that is the video processing layer. And then there would be the client application layer, which would have the set-top boxes, web portal, mobile phones, applications, connected TVs, connected devices, and so on. And of course, there is the CDN layer as well. Now, we talked about the metadata, data, and control layer, which is nothing but the backend. So that is the backend which you can build in microservices and so on. Video processing layer, which we talked about in this and in the previous session. There would be various pluggable layers of the ecosystem which can make the entire thing work together well, with various campaigns happening, CRMs for managing the third parties, for sending out push notifications to users and so on. So that is one layer. And then obviously you have the client layer and the CDN where you store all your static assets. So that is all about the OTT platform architecture. If you have questions, ask me in the comments. I'll obviously try to create another video to answer those questions in specific. Thanks a lot for your time. Have a good day.